Hey, this is Genesis. How are you guys doing? Well, today I'm going to talk about rational functions. Now, for rational functions, you need to know the following. You need to already know how to get the zeros of polynomials. You need to know how to do polynomial division. This includes long division and synthetic division. Another thing that you need to know is you need to know how to factor quadratic equations. And you also need to know how to find the domain of a function. And last but not least, for this lesson, you should be familiar with, I didn't write it down, you should be familiar with the remainder theorem and the factor theorem. And you need to know how to write in interval notation. So I would like to introduce you again to Omega Math. OmegaMath.com is a company that helps you learn how to do math. Now, I've been using Omega Math for around about 2 or 3 years now, and or more. They've been helping me with math, and they help me learn everything I know. They have algebra, pre-calculus, geometry, trigonometry, calculus, even high school algebra, anything that you need for math. They're really good. They're really good with it. And again, I learned everything I know from them, and I recommend, highly recommend them to you over anything on the web, including I'm not gonna, I'm not sure if I should mention the name, but yeah, I highly recommend them over anything in the web because they help me, and if they can help someone like me, I'm sure it can help someone like you. Okay, let's begin this lesson. First, I would like to introduce you to Genesis's 10, that's me, Genesis's 10 commandments for graphing rational functions. The first thing is thou shalt find the domain. The second thing is thou shalt simplify the function. And here's how you simplify the function. Okay? You get this. Let's say this is an example. You have 2x plus 2 over x plus 2 all squared. So you would simplify in this way. You would get this, and you would factor out the 2. Find anything in common, and you cross this out because they're the same here, and it will equal to that. And that's how you would simplify a function. The next commandment is thou shalt find holes. I'll explain to you what that is later. But thou shalt find holes. Okay? Next commandment is remember the vertical asymptotes. They divide the graph. Remember the vertical asymptotes. They divide the graph. It divides the graph. Fifth commandment. Get the horizontal asymptote. Sixth commandment. Get the slant asymptote. It's also called the oblique asymptotes in some textbooks. But get the slant asymptote. Okay. 7. Determine the x-intercept. 8. Commandment. Determine the y-intercept. And the ninth commandment. Determine any symmetry. That is, when you do that, you test even, you test for odd. If it's even, if it's not even or odd, it's neither. And the last commandment that will help you out when you are trying to graph the rational functions is to plot one or more points to determine the graph's location. This is the 10 commandments. Genesis' 10 commandments for graphing rational functions. So we are going to, first, when you graph rational functions, right? We need to know, well, before we get into it, we need to know what a rational function is. A rational function is when you have two polynomial functions, right, that are divided by each other. For example, this is a rational function, and it's going to come up later. invisible one there. This is a rational function. Another example is this. Another one. Here's another one here. These are all rational functions. You have polynomials in the numerator, and you have polynomials in the denominator. But one thing that you need to know is that rational functions themselves are not polynomials, but they only contain polynomials in the numerator and one in the denominator. One on top and one on bottom. But they're not them in and of themselves rational functions. Now, once upon a time, you learned about something called proper fractions. Once upon a time, you learned about something called proper fractions. Right? Remember that one? They look like this. 1 over 2 or 4 over 9. Right? The numerator is always less than the denominator, right? And you also learned about improper fractions. Remember that? And basically you have, it'll look like that, 5 over 2 or 3, 4 over 3, right? Or 11 over 2. And basically with the improper fractions is that the numerator is greater than the denominator. And let's call this one, it's not the proper name, but now, for this lesson, let's call this one, the next one I'm going to put equal fractions. Okay? And equal fractions, I'm calling this equal fractions. They for this lesson, they may not be called that. You have 4 over 4, right? Or you have 5 over 5, or you have 8 over 8, okay? That's when the numerator is equal to the denominator, right? The numerator here is less than the denominator, and the numerator here is greater than the denominator, right? Now, just as you have proper, improper, and equal fractions, well, we have also proper, improper, and let's call it equal rational equations. And the difference is that instead with rational equations, like the one you have here, you see 4x, 2x squared minus 8. Instead of looking at the terms, the real terms here, you're going to look at the powers here to determine and to interpret what these rational equations really represent. So you're looking at the highest power here to determine what they are. Now, in order to graph a rational function, you have to know a few things. You have to know what an asymptote is. And basically an asymptote are these invisible lines. They may go horizontal, right? Those horizontal asymptotes. Or they may go vertical. They may go vertical like this. We call these vertical asymptotes. And sometimes the asymptotes go this way. Let's say, so this will be a vertical asymptote, right? This will be a horizontal asymptote, right? And this will be a slanted asymptote. Slant asymptote here. Sometimes your textbooks call them oblique. Oblique asymptotes, right? And this is x and this is y, right? So, and when you're drawing stuff on the graph, when you're drawing on the graph the function, you would draw it let's say right here, the graph will come close to the asymptote, but it will never ever quite touch it, right? Never quite touch it. So if you start here, it would follow the asymptote like that. Actually, these all won't exist at the same time, but I have it up there for you to see, how it works. Okay, it's not going to be like this in reality. So you would go like this, okay, and you would just follow along the asymptote line. Same thing with this one, okay. Same thing with this one. You're actually graphing it, all right. Now for horizontal asymptotes, if you're graphing for a horizontal asymptote, you can go across the horizontal asymptote. Okay, you can actually go across the horizontal asymptote, right? But the further you go away from the bigger the function, right? That passes through the asymptote, it will just hug the asymptote, right? Like this. It won't go past it. Again, right? Okay, so for vertical asymptotes, you can't go across the vertical asymptotes. It's impossible. Vertical asymptotes is like a big division wall. You can only follow the vertical asymptotes up, right? Slanted asymptotes, same way. You cannot go past a slant asymptote. It's like a big wall blocking you, okay? It's impossible to go past an oblique or a slant asymptote. So that's to give you a heads up about when you're graphing them. Okay, now the first thing we want to do when we're graphing rational functions, remember our 10 commandments, write them down and keep them with you at all times. The first commandment is thou shalt find the domain. Okay, so how do we find the domain of a function? This is something that you should know from previous lessons or from your algebra, right? That's really basic. This is how you find the domain of a function. Just a little review of how to find it. Okay, you have x squared minus 5x plus 6, right? Well, when you're finding the domain of a function, you have to ask yourself two questions. Could there be division by 0, right? If there could be division by 0, then it will, if 0 is in the denominator, this will be an undefined. This will be it will be undefined number. It just wouldn't exist, right? You can't have 1 over 0. It's illegal in math. It's illegal. Just remember that this is illegal in math. You cannot have that. Okay, you just can't do that. You can't have 1 over 0. So we don't want zeros in the denominator. We don't want zeros in the denominator. So we want to eliminate everything that will make this a 0. The next thing you want to know is if there's a square root in the denominator or a numerator, and there's not, right? So could there be division by 0? So we have to find out, we have to factor the denominator, right? If we factor this, it will look like this. Okay, then we pull out these two things. Our two factors here, that's a factor and that's a factor. These two things are multiplications, so it's a factor. Set them equal to 0. Set them equal, x minus 3 equals to 0. Okay, and solve for x. That crosses out. X will be equal to 2. Solve for x. That crosses out. X will be equal to 3. Okay. Now that we got x is equal to 3, x is equal to 2, these are the things that we don't want. These two answers are we don't want. If we put a 2 in x and all the x's, we'll have a 0 in the denominator. Look what happens. Look, let's see. X minus 1. Let's put a 0. Let's make this x2. Well, make all the x 2. So it'll be 2 squared, 5, 2 plus 6, right? Solve for it. See, this will be 4. That will be negative 10 plus 6, put the positive together. 6 plus 4 is 10 minus 0. That's going to be 0. So it's going to look like this. x minus 1 equals over 0. If x were 0. And guess what? Look, we have a 0 in the denominator. We don't want zeros in the denominator. That's illegal in math. So guess what? That's not going to be in the domain of the function. These two numbers won't be in the domain of the function. So we're going to eliminate these from the function. So our function, the domain of this function would be all real numbers except x is equal to 2 and x is equal to 3. Okay? And here's how you write it in set notation. You may see this in a test. All of x, that means all of x, and this line means where, all of x where x is not equal to 2, x is not equal to 3. We don't want those because that will make the bottom 0. Okay, that's set notation. Interval notation, you take these two numbers here, right? I like to do this to help you draw set notation. That's invisible infinity. I mean negative infinity. That's positive infinity. That's 2. That's 3. Okay, set notation is every number from negative infinity to, comma means 2 for you guys listening to this video. 2. Right? Or this U-shaped thing means or, okay? 2. This you have this here, you have that here, yeah. So you have 3 different 3 different regions. So from or 2 to 3, or 3 to infinity. Okay. That's how you do interval notation. I'm not going to spend too much time here explaining the ins and outs of interval notation. You can learn that somewhere else. And this is not, it's not the purpose of this video. The purpose of the video is to help you understand how to get graph rational functions. Okay. Let's try another one. This is important too for you. I'm going to get this here to refresh in your memory on how to get the domain of this. 2x x squared plus 4. Okay, let's ask yourself, could it be division by 0? Let's take this here, set it equal to 0, right? Let's solve for x. Okay, x squared equals to negative 4, right? Now we're going to square root both sides. Remember, when we square root both sides, we have to have plus or minus the square root of that number that we put on the other side, okay? So if we keep solving it, our x's, square root of x squared is x, okay? Equals to plus or minus the square root of negative 4. The square root of negative 4 can be broken up in this way. Remember, you still have plus or minus, right? This negative is actually negative 1. 4. Okay? Now the square root of 4 is 2. Right? The square root of 4 is 2. And the square root of negative 1 is I. That's something you have to remember. Anything inside the square root that's negative 1 is going to be I. 2I. That's the answer. Now, this is an imaginary number. Right? These are imaginary numbers. Plus or minus 2I, right? So in this case, there are no real solutions. That means they don't exist. They don't exist, okay? So this means that there's nothing that you can put in x that will make it 2x equals to 2x divided by 0. Nothing you can put in there, okay? There are no real solutions for x. There only are imaginary solutions. You know why? Because they don't exist. You can't make it 0. So that means that the domain here of this function is all real numbers. And you can write the domain all real numbers like this: negative infinity to positive infinity. That is interval notation. Okay, great. Let's move on. There's something I want to show you too. Another thing that you should always keep in mind. Let's look at this problem. Okay. Function of x minus 1, x squared minus 5x plus 6. X minus 2, x minus 3. Okay, this is this is not the same function as, let's call this g of x equals to x minus 1. Well, what am I talking about? They are different things. Why am I picking on this one? Okay, remember with the factor form of this, look at this, factor it. The factor form of this looks like this. Let's see. I'm going to have okay, we factor that. That cancels out, that cancels out, that cancels out, that cancels out. And so the factor form of this looks like this. Ta-da! That looks just like that, doesn't it? They look the same, don't they? But guess what? These are not the same. Oh my gosh. These are not the same. Do you know why? Because their difference. Their difference is their domain. Their domain is totally different. Their domain is different. Okay, the domain is different. The domain of this one here is, as you saw here, all real numbers, right? All real numbers, except, what do we have here? X plus 2 and x plus 3. All real numbers except x2 and x and 3, 2 and 3. This here, on the right side, the domain is just all real numbers. All real numbers. So if you plot a graph of the first one, right? If you plot a graph of these two, they will have a graph that looks exactly the same. Look at this. Right? They will look the same, but one of them has a hole in it. Just like that, a big hole. The numbers that we cancel out during the process of factoring this thing and finding the domain, right, are the numbers that are holes. And in this case, what did we cross out? We crossed out x minus 2 and x minus 3, which happens to be x equals to 2 and x equals to 3. So these two numbers, because we crossed them out, because they were crossed out, right, they are going to be our holes. And this is something to always remember, right, that the common factors need to be divided out first, and then the leftover x values are the roots. They're going to be the vertical asymptotes. So we'll get to that one later. Just throw it out there so you hear it. Anyway, but if you don't understand it, it's okay, because you will as we go along. So if we graph this function, remember x equals 2 and x equals to 3 are going to be our holes. Okay, x equals 2, x equals to 3. So we have, we start at -1, right? because I mean this ultimately is y equals to x minus 1, right? So the y-intercept is x is negative 1, right? And our slope is 1, right? So we go up 1, we go across 1. We go up 1, we go across 1, right? Then we draw the line, right? Then we go up another 1, then go across 1, which is 3, okay? 4, 1, 1, right? These will be our dots here. Okay, our holes, we're going to draw a line whoop, to this one, then through 1, and then when we get to 2, oh my gosh, look. When we get to 2, look what happens. There's a big hole here. You see that? Then we go to 3, oh my gosh. There's another hole, another big hole here. 1, 2, 3, 1, 2, 3, right? 4. Then we connect the dots. We keep going. So look, these are the holes. And look, it fits the domain. All our numbers except -2, except 2 and 3, holes 2, 3, right? 2, 3. And look with this one on the right side. Let's try to graph this one. There are no restrictions, right? Y equals to mx plus b, right? Y equals to x minus 1. Okay, let's graph that one. Negative 1, 1, 2, 1, 1, 1, 1, 1, 1, draw a line. There are no restrictions, like this one. So that's what makes these functions different. The domain is different, okay? So next time, watch out. Look for those holes, okay? Look for those holes. The next thing we need to know in our 10 commandments, after we find the domain, is simplify the function, like so. And find after thou have found the holes, you need to remember the vertical asymptotes. These vertical asymptotes divides the graph, okay? Hey guys, so the vertical asymptotes our VA leftovers are vertical asymptotes. Well, they're leftovers in the denominator, and they divide the graph into different sections. Okay, for example, let's do an example so that later we'll put it together. Okay, 4x squared over x plus 2. Well, what is our domain? Our domain is, as we're doing our domain, we notice that x plus 2, we take x plus 2, set it equal to 0. X will be equal to -2, right? And remember, we see that there are no common factors. Great. To be divided out. So our leftovers in the denominator are x plus 2. We got x minus x is equal to -2, right? That's a root. So we don't want that. So the domain is going to be all real numbers except x minus 2. So all real numbers except -2, right? Guess what? That left over in the denominator is going to be our vertical asymptote. Okay? So our vertical asymptote is x is equal to -2, okay? And here's how it will look on the graph. We have our graph here. Whoop, that's our graph, that's our y. Whoop, that's our x, right? We have our 1, -1, we have -2, we have -3, we have 2, we have 3, right? X is equal to -2 is a vertical asymptote. Look what happens. X is equal to -2. We have area 1. We have this whole area, this whole thing here on this side, this left side of the asymptote, x is equals to -2 is area 1. This whole side on the right of the asymptote is area 2. Okay, let's try another one. 6x squared over 3x squared minus 12. Well, remember, the first thing we need to do is find common factors that need to be divided out, right, of this function. Call this f of x function, right? And then the leftovers in the bottom will be our roots that we can find, right? And those roots will be our vertical asymptotes. Well, it's already factored, right? We can't factor anymore. So we're going to just take the bottom out, right? Solve for x. Take the bottom out here. We can solve for x in this way, or I can factor it. I'm going to factor it out. You know what? Kind of lazy here. X squared minus 4, right? We factor this further to x minus 2, x plus 2. So if you try to solve for the domain, try to find the domain, you set all these equal to 0, the domain will be equal to, well, this will be equal to 2, this will be equal to -2. We don't want those. We don't want these. So our domain is all real numbers except x is equal to 2, x is equal to -2. Okay? If you put this in interval notation, right? -2, 2, -infinity, infinity, right? All real numbers except 2, that means like -2, or -2 to 2, or 2 to positive infinity. Set notation, you may see this on some people's class. All x except x is equal to -2, x is equal to x is not equal to 2. Okay, you'll see that. And look, since we know this, how's it going to look like on the graph? On the graph, it'll look like this. Okay, you'll have your x-axis, you have your y-axis. This is 1, this is 2, this is 3, this is -1, this is -2, this is -3, right? And our vertical asymptotes, they will be whatever is not in the domain. So our vertical asymptotes are going to be x is equal to 2, x is equal to -2, right? Let's put them over here. X is equal to 2. Goes on forever. X is equal to -2. Goes on forever. Well, how many sections did the vertical asymptotes divide this graph into? It divided into 3 areas this time. The first area we have is area 1. Area 1. This area here is area 2, right? And this area here is area 3. So we have 3 areas. This area here, 2, and 3. Okay, we're going to do one more. For x, 2x squared minus 8 minus 7. Okay. Well, let's look for the domain. Remember, the first thing we got to do is find common factors needed to be divided out, right? Okay. Find common factors that need to be divided out. And then the leftover x values are the roots, the values of the asymptotes. I mean, the vertical asymptotes. Okay, so we're going to take this out, set it equal to 0. Solve for x. X will be equal to 7 if we put it on the other side, right? Take this out, set it equal to 0. or we can factor it, right? We'll factor it out, okay? So 4, right? I can simplify this further. X will be equal to 2. X will be equal to negative 2. So we don't want any of these. It will be all real numbers except for these things that we got here, right? All real numbers except these things will be the domain of this function. Well, whatever is not in the domain, and also that are left over, is going to be our vertical asymptotes. And they are x is equal to 2. Well, I need to put this, the domain is all real numbers except x equals to 2 and x is equal to negative 2. Okay, that's the domain. But the vertical asymptote is x is equal to 2, x is equal to negative 2, and x is equal to 7. Whatever is not in the domain is going to be your vertical asymptote. And if we graph this baby, okay, this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 7, 8, 6, 5, 4. Okay, so x will be equal to 2, negative 2, and 7. Now, how many sections did the vertical asymptotes divide this graph into? How many sections do we have? We have this section here, this whole thing here, that's area 1, area 2, area 3, and area 4. We have 4 areas. 1, 2, 3, 4 areas this time. And remember, when you actually graph it, you can't intersect across here. You can't go across this thing, right? You cannot. It's impossible. You just can't do it. These are walls of division, right? Walls of separation. So you just can't do it. Okay. Now the next thing you need to know is how to get the horizontal asymptote, and guess what? It's part of the my 10 commandments to you for graphing rational functions. So after remembering those vertical asymptotes, after dividing the graph, right, into walls of separation, we need to get the horizontal asymptote. Remember that. So we're going to try to get the horizontal. Asymptote. And guess what? Horizontal asymptotes are special because the graph can go through a horizontal asymptote. It can go right through it. But it can't go through the walls of separation with the vertical asymptotes, only with the horizontal asymptotes. Now, remember I was telling you about, right? I was telling you about proper fractions, right? Proper ratios. You have this, you have 1 over 5, right? You have 2 over 4, right? Something like that. Those are all proper because the numerator is greater than the denominator, right? Well, the same thing with proper rational functions. Proper rational functions, you have, let's say you have this. You have a x to the power, let's call the power n. Let's call this power n, okay? This is going to be the highest power. Divided by, and this is going to be just a number, like coefficient. It could be 1 or 2. This is a different number. Let's call this number b, okay? X to, we're going to call this highest power m, okay? Just to separate them, make them different. This is going to be your other highest power, okay? So n is less than m, right? Like this. For example, if we have x to the 2 power, that's our n, and the bottom we have x to the 3 power, I'm going to call that m, okay? 2 is greater than 3, right? N is less than m. This is going to be a proper rational function. And if it's a proper rational function, then by default, y is equal to 0. Okay? Y is equal to 0. Now the next one is the, I call it again, equal power rational function, right? Equal power rational function. For example, you have 4 over 4, right? 4 over 4. Or you have, 2 over 2 or 8 over 8, okay? Those are equal ratios, right? And so equal power rational function, or rational function is ax to the, again, I'll call this n power, right? Bx, let's call this m power, right? So in this case, n is going to be equal to m. For example, you have x to the 3rd power over x to the 3rd power, right? So the powers are equal. And if you have this case, right, then y will be equal to the coefficients, a and b. A divided by b, okay? A divided by b. So if a were 4 and b were 1, if a were 4 and b were 2, a and b will equal to 4 divided by 2, which is 2. If there weren't anything here, it just says x, right, and if 4 is on top, then there's always an invisible 1 here, isn't there? Remember that. There's always an invisible 1 there, so it'll be 4 over 1, right, which is 4. Good. So it will automatically be y is equal to a over b. That will be your horizontal asymptote, right? That's your horizontal asymptote. So first one, proper rational function, where if n the top power is less than the bottom power, y is equal to 0 is your horizontal asymptote. Equal powers, n is the same as m, right? Like this. Then you'll take your coefficients and divide them. Y will be equal to a divided by b, right? And there's a last thing. It's called the improper fraction. You know those. 5 over 2, right? 4 over 3, you know those. So we have ax to the nth power divided by b, another number time, to the x to the n, another power, right? And this time, n, the top power, is greater than the bottom power, right? Then we have no horizontal asymptote. No horizontal asymptote, babes. Okay? Now, if it's improper, right, and n is greater than m, there is no horizontal asymptote. And if there is no horizontal asymptote, there could be a slant asymptote. Yes, there could be a slant asymptote. And sometimes they call slant asymptotes oblique asymptotes in your textbooks. Some textbooks, not all of them. Okay? So if there's no horizontal asymptote, then there could be a slant asymptote. I'm not saying that there is a slant asymptote. I'm just saying that there could be a slant asymptote. So you have this, right? There could be a slant asymptote for all of these babies. Okay? And if so, if you have an improper, right? For if you have an improper, right? Then you have to do something called polynomial division. Polynomial division, and you all remember that from previous lectures, right? And after you do your polynomial division, you ignore the remainder. Ignore your remainder. And your answer is the q of x. Your answer will be, I just give you concept. We'll do the concepts, so we'll do a real one later. Your answer will be your q of x. Ignore your remainder, right? And your q of x, your answer must have a power of 1, okay? It must have a power of 1. So it must look like this. Mx, right? Power of 1 plus b. Sometimes you may never have a b, okay? But it must have a power of 1, or else there is no slant. So you can have rational functions that have no horizontal asymptotes and no slant. And no slant, okay? So let's do one. So we're going to get the slant asymptote, also called oblique asymptotes. Okay. Is there a slant asymptote? Well, let's look. We look at our powers, right? We look at our powers. We see that for the highest power in the numerator is greater than the highest power in the denominator. So n is not less than, n is greater than m, isn't it? So that means there could be a slant asymptote. And in order to figure out if there's a slant asymptote, we have to do what? We have to do polynomial division to find out if there truly is a slant asymptote. Of course, there's shortcuts, but for now, you need to understand what's going on. So remember, whenever we're doing polynomial division, we have to make sure the numerator and the denominator look like this. X is 5. It can go to any highest power, right? Whatever the highest power starts out of, it has to go down in order. 5, 4, 3, 2, 1. Zero, right? Same thing with the numerator. It must be 6. It doesn't matter. 5, 4, 3, 2, 1. X plus x 0. And the reason why I left 0 up here is because anything to 0 power is 1. Okay, anything to the 0 power is 1. 2 to the 0 power is 1. 5 to the 0 power is 1. This jug of milk here to the 0 power is 1. So this will be 1 on here, right? Or let's call this rather a constant, because what you're going to have here, you're going to have like a number like 2, right? So it'll be 2x to the 0. And this will be 3x to the 0, for example. So x to the 0 power is 1. Right? 2 times 1 is 2. It's constant. It will be a constant. So we have to put in this order. So do we see that here? 4, 3, 2, 1. We're missing stuff, aren't we? Right? Uh-oh. So let's first write down what we're missing. 4. If we're missing something, we have to put something called placeholders in there. Placeholders in there. Our placeholder is going to be a 0. We're just going to put 0. 0x, okay? And what's next? 0, we have 4. It's going to be 3. Right? We have 2. So it's not going to be plus. Aha. It's going to be negative x squared. Negative x squared. And what else are we missing? We're missing a 1. So we'll put another placeholder here. Right? 1. And we're also missing the 0. Plus 0 to the x to the 0 power. Oh, we can leave this one as 0 because x to the 0 power is 1. 0 to 1. 0 times 1 is 0. So we'll leave it like that. Look, the bottom one. Look. x to the third minus, there's 3, 2. We're missing 1. So we'll put a placeholder here, 1, and 1 to x to the 0 power. Yep, we got it. We're good. Now we can conduct polynomial division. So let's go. X cubed minus x squared plus x to the 1 power plus 1, right? 4 x to the 4th power plus 0x cubed minus x squared plus 0x to the 1st power plus 0. So what times x cubed equals to x4? 4x. 4x times x cubed is 4x to the 4th power. 4x times negative x squared is going to be negative 4x cubed. 4x times x times 0x to the 1 power is going to be plus 0x to the 2nd power. And 4x times 1 is going to be positive 4x. Now we're going to subtract it, right? We're going to subtract it. So everything inside here is going to be subtracted, right? So that means all of our terms inside, we're going to distribute this negative, this red negative 1 into all the terms. So this will change from, I'll keep it positive. This will change from positive, cross it out, to negative. This will change from negative to positive. This will change from positive to negative. This will change from positive, cross it out, to negative, right? Now we're going to simplify. When this crosses out, right? That becomes 0. There's nothing. 4 plus this is going to be 4x cubed, right? Signs don't change, remember? This plus this is going to be negative x squared. This plus this is going to be negative 4x. Okay, now what times x cubed equals to 4x cubed? Yeah, it's going to be positive 4. Positive 4 times cubed is going to be 4x cubed, right? 4 times negative x squared is going to be negative 4x squared. 4 times this is going to be 0 x, right? There's x there, so 0x. 4 times 1 is going to be, well, you know what? I forgot to bring down this 0 here. Sorry about that. Got to bring that down. So 4 times 1 is going to be positive 4. Then we're going to subtract it. So all the terms, all the signs here will change. This is positive is going to be negative. This is negative is going to be positive. This is positive is going to be negative. This is positive is going to be negative. And then we simplify. That's going to cross out, right? That's going to become positive 3x squared. That's going to become negative 4x, right? To the 1 power. And this is going to be 4. Now we ask ourselves the question again. What times x cubed equals to 3x squared? Nothing. We're done. We are done, guys. So remember, this is f of x. This thing inside, this long thing is f at x. This thing is your divisor, right? You just divided f of x with this. And this is your q of x. This here is your remainder, r at x. So remember how you write it? dx over, f at x over dx equal to q at x plus remainder over your divisor. Remember, that's how you write it. So let's write it that way. We have f of x equals to q of x, our answer, which is 4x plus 4 plus our remainder, which is 3x squared minus 4x minus 4 over our divisor, x cubed minus x squared plus 1. Now what about, that took a long time. What about our slanted oblique? What about that? Well, in order to graph it, right, you have to remember this. Ignore your remainder. Trust me on this one. Ignore your remainder, right? And we should get for a slant asymptote, the answer must be your answer must have a power of 1 or else there's no slant, right? Your answer will look like this: y is equal to mx plus b, right? And look what we have here. We have, if we ignore our remainder, y equals to mx plus b, right? So it will be y equals to 4x plus 4. And guess what? We can graph that. Our slant asymptote will look just like this. Okay, so we start at 4. 1, 2, 3, 4 here. Then our slope is 4. So we go 1, 2, 3, 4. 1, 2, 3, 4. And over, sorry, we go, up 4. 1, 2, 3, 4 over 1. Right? And then our slant asymptote will look like this. Do we connect the dot? Forever like this, forever like that, forever, right? And guess what? When we take this equation here and we try to draw a graph on here, right? It doesn't matter where it is now, but when we try to draw it, the graph will get close to the asymptote, but it won't quite touch it. And guess what? You can't go across it. You cannot go across the asymptote. It's like a wall, like the vertical asymptote. You can't go across it, okay? Good. Nothing can touch it or go across it. This kind of sums up all the 10 commandments that you are not familiar with. So remember, kind of to summarize, in order to graph rational functions, first you must find the domain, simplify the function, find the holes, find the vertical asymptotes, which divides the graphs and the big walls of separation, and then the horizontal asymptote. If there's no horizontal asymptote, there could be a slant asymptote, so you conduct polynomial division, right, to find it. Then you also need to determine the x-intercept and the y-intercept. Then you find out if there's symmetry. So you test if for odd symmetry, and then you test for even symmetry. And then you plot one or more points to determine the graph's location. That's how you do it. So let's try to graph some rational functions.